Welcome. In this presentation, we'll explore how text can be transformed into images using modern AI techniques. I'll give you an overview of the topics we'll cover, including the motivation behind these models and their impact on image generation. We'll start by introducing the key papers and the overall goals of this session. This slide shows the problem we are trying to solve. The goal is to generate an image for a given text prompt. For example, how do we turn the text from an oil painting of a cat in pastel style into an actual image of a cat that matches both the content and the style? One way to do it is by using a latent diffusion model. In this presentation, we'll cover two papers. The first paper from the study guide introduces latent diffusion models, which compresses images with a lower dimensional latent space and uses diffusion and denoising to generate an image. The second paper investigates stable diffusion, which is a latent diffusion model, and generates image from a text prompt. The paper investigates where human-like semantic resides in the stable diffusion model. At the end of this presentation, I would like you to understand how these latent diffusion models work and how it's able to interpret the human semantics of a text prompt when generating an image. This is achieved by explaining the latent diffusion model and also the stable diffusion model. Last, we'll dive into how stable diffusion handles semantics understanding of a text prompt. Let's start with the first paper with the title High-Resolution Image Synthesis with Latent Diffusion Models. This paper introduces latent diffusion models for image synthesis, which improves computational efficiency and images synthesis task of diffusion models. In the next slide, we'll dive into how these diffusion models work. First, what are diffusion models? A diffusion model tries to learn how to reconstruct an image, X in this case of a cat, by gradually adding Gaussian noise resulting into a garbage image XT. This process is also called the diffusion process. Then it trains a denoiser to predict and remove that noise, resulting into a reconstructed image X tilde. The goal of the training is to minimize the error between the reconstructed image and the original image, such that it can faithfully reproduce the image. At the training stage on the previous slide, we learned how to reconstruct a cat from a garbage image XT. At inference stage, we can reuse this to generate a new garbage image XT prime and reconstruct it into a different cat using the same denoising process. There are different types of diffusion models. The one specifically discussed in the paper is the pixel-based diffusion models, which operate at pixel level. The disadvantage of these models is that they are computationally expensive at training time and slow at inference time, since they have to iterate over each pixel. Furthermore, it also iterates over pixels which might not capture the relevant details to reconstruct the image, thus making them inefficient in handling of imperceptible details. Lastly, since they operate in pixel level, if you increase the resolution, the scalability is also a problem. To resolve the limitation of pixel-based diffusion models, the paper introduces latent diffusion models. The idea between the latent diffusion model is to encode the image into a lower dimensional latent space Z, indicated green in this picture, using a variational autoencoder. This is also called perceptual compression, where it removes imperceptible details from an image. The fact that the diffusion process, indicated also in green, operates at a lower dimensional level makes it computationally more efficient. Furthermore, the denoising process consists of a concatenated set of units which encode the semantic meaning of the image. Lastly, the denoising process can also be guided by conditioning the units on other modalities such as text or images, and that's where the text to image generation part comes in. This slide gives a high-level overview of how text-to-image synthesis works using a latent diffusion model. It starts with a random latent noise ZT and a text prompt, in this case a photorealistic cat. The text prompt is encoded into the latent space and conditions on the units of the denoising process. After multiple iterations in the latent space, the image is decoded into the pixel space and resulting in the image of the cat shown on the left. This slide shows the same process, but then plotted on the LDM architecture. It starts out with the text prompt and the ZT random noise generated image as before. The text prompt is encoded into a text embedding, which can be either combined using concatenations or via the cross-attention models of the UNet. This combination steers the denoising process into incorporating the text prompt in finally decoding and generating the image of the cat. In the previous slide, we saw that the UNets can be conditions on a text prompt, but it can also be conditions on different modality, resulting into latent diffusion models supporting different types of image synthesis tasks. We will highlight a few of those. First, text-to-image generations, which we already saw in the previous slide. Furthermore, also inpainting, which fills in specific regions of an image using a mask. This can, for example, be used to remove objects or persons from an image. And also super resolution, which upscales the resolution of a low resolution image. Let's now dive into the experiments conducted by the researchers of this paper. They conducted multiple experiments for each image synthesis task shown on the previous slide. To limit the scope of the presentation, we'll just focus on the text-to-image synthesis tasks. For training evaluation, they use different data sets, namely Leon and MS Coco. The training was performed on a 1.5 billion parameter latent diffusion model, which was conditioned on using a BERT tokenizer for the text prompts. The model was evaluated on the MS Coco benchmark datasets, which was also used in different other papers. And the metrics they used were FID and the IS scores. The FID scores measures how close the distribution of the generated image is to the real image. So the lower the value, the lower the error. The IS score indicates how meaningful and diverse the images are. The higher the score, the better. In the end, the result for text-to-image generation showed that LDM performed on par with other state-of-the-art models such as Glide and Make a Scene. The overall conclusion was that latent diffusion models improve the computational efficiency compared to pixel-based diffusion models, and that UNets in the latent space enable a wide variety of image synthesis tasks as shown earlier. Let's now dive into the second paper with the title "Clip is all you need for human-like semantic representations in stable diffusion." A mouthful. This paper investigates how stable diffusion can generate images which aligns with human interpretations of a text prompt. In other words, why does a text prompt like an oil painting of a cat generate an image which matches our expectations? As the title mentioned, it conducts the experiments on the stable diffusion model. Stable Diffusion is a popular text-to-image generator based on the Latent Diffusion Model architecture, as shown in this slide. It uses the optimized clip text encoder to embed the text prompt and then injects the text prompts on the UNet like explained before. The idea of this paper is to investigate different measure points in the latent space. I indicated it using purple, and it tries to check for each measure point in the latent space if these value can be used to predict human-like attributes, or in other words, if it encodes semantic information. I'll explain this further on the next slides. So the main research question in the paper is, where do human-like semantics live in the latent space of the Stable Diffusion model? It tests this by using a technique probing, which we'll elaborate on the next slide. It uses the mTurks dataset, which is a labeled dataset where X is a noun and Y are human ratings. For example, a noun could be the text prompt like bear, and human ratings are human rating attributes like large or scary. If you compare it, for example, to a whale, large might be 3 for a bear and 5 for a whale, and scary might be 5 for a bear and 2 for a whale. This way, these nouns can be semantically encoded using those human rated attributes. The hypothesis is that if a measure point in a Stable Diffusion has semantic meaning, it can predict these attributes of the mTurks dataset. Now let's dive into how this actually works. The research of this paper is performed in two steps. First a training stage and then a validation stage. This slide shows the training stage. The training stage runs the Stable Diffusion model for each noun from the training set and then collects the generated values at the measure point in the latent space, indicated purple in the here in the slide. Afterward, it trains a linear rich classifier for each measure point to predict the ratings Y, these ratings, on the collected values X for each measure point. The result of this training phase is a set of trained classifiers for each measure point, which can be used later on in the validation stage. The second part, the validation stage, runs the Stable Diffusion models on the nouns of the validation set and also collects the values at each measure point. But instead of trying to train the linear rich classifiers, it reuses the trained classifiers earlier and now tries to predict the ratings Y for the collected values X and the trained weights W from the previous stage. The result is a set of predicted ratings for each prompt in the validation set. It then compares the predicted ratings to the ratings in the validation set itself based on two measures, the root mean square error and the cosine similarity. The lower the error and the higher the similarity, the better the measure point encodes the human-like semantics in the text prompt. This slide shows the results and conclusion of the paper. The result of the paper is that the best alignment occurs right after the encoding of the text prompt using the clip text encoder, which is this dot in the architecture. Furthermore, the semantic alignment degrades gradually the more iterations are performed on the UNet in the denoising stage. The paper then concludes that the clip text encoder, so this part, supplies the human-like semantics of the Stable Diffusion Model, and the UNet primarily acts as a visual decoder. Thus, the semantic understanding in the Stable Diffusion comes mainly from conditioning outside the latent diffusion model. Last, we'll have a look at the overall conclusion of both papers and have a short discussion on the results. So the overall conclusion is that latent diffusion model reduced the computational load while preserving the image quality compared to previous diffusion models. Furthermore, the cross-attention mechanisms, or UNets, allows for a variety of image generation tasks with the latent diffusion model. And last, with the stable diffusion model, the semantic understanding of this model lies in the clip text encoder, as shown in the previous slide. That paper used the probing technique to explain the success of the stable diffusion model, but it might be also applicable to other text-to-image generator like Glide or GAN-based models. And it might not only help to understand why a specific model is successful, but also indicate where it might struggle with the semantic encoding, thereby improving or indicating where you can improve the model. Furthermore, if you use, for example, the stable diffusion model and have a newer version of the clip text encoder, you might compare the results of the semantic encoding to try to see if the performance on that part has improved or degraded. And based on that, you can decide or evaluate the new architecture. Overall, this technique contributes to the interpretability of the inner workings of diffusion models, which I think is a good thing for Gen AI. Last, I have a peer review question prepared based on the previous two papers. The question is, what role does the variational autoencoder, also called VAE, play in the latent diffusion model, and why is it critical? Good luck, and thank you for listening.